limits. The coverage probability is simply the probability that theta lies between L and U. Okay? And finally, the coverage length. The coverage length is the difference between U and L, which is this, right? Then I talked about percentiles. I talked about percentiles on Monday. For the normal distribution, the percentile are defined like this. So this is the shape of the density of a standard normal. You should take a point along the x-axis, and if there is an area of alpha to the left of that point, then this point is denoted by z subscript alpha. Right? And in this graph, you should have an area of 1 minus alpha in the middle, alpha by 2 on the left tail, and alpha by 2 on the right tail. Then this point, by definition, is z subscript 1 minus alpha by 2. And this point, by definition, is z subscript alpha by 2. Okay? That's for the standard normal distribution. Right? For the student's t distribution, which we talked about a long time ago, the concept is the same, right? This is the shape of the student t PDF, right? You should have a point here, and if there is an area of alpha to the left of it, then you denote the point as t subscript A. A is the degree of freedom, comma alpha. Alpha is the area to the left, right? And looking at this graph, if there's an area of 1 minus alpha in the middle, alpha by 2 in the left, alpha by 2 in the right, then this point here is TA 1 minus alpha by 2, because 1 minus alpha by 2 is the area to the left of this point. And this point is TA comma alpha by 2, because alpha by 2 is the area to the left of this, right? And because of the symmetry of the t distribution, these two are equal except for the minus sign. And the same thing here, because the normal PDF is symmetric around 0, these two are equal except for the negative sign, right? And then I talked about, I'm kind of summarizing what I did on Monday. I talked about the chi-square distribution, which we talked about a long time ago. This is the typical shape of the PDF of a chi-squared. And if there's a point here, and if to the left of it there's an area of alpha, then this point is denoted by chi-squared subscript A comma alpha. Alpha is the area to the left. And in the second graph, if you have an area of 1 minus alpha in the middle, alpha by 2 on the left, alpha by 2 on the right, then this point is denoted by this, and this point is denoted by this, right? So these are notations, and after introducing the notation, I started talking about confidence intervals. I only managed to do one because I need to do more today. All right, the first confidence interval I talked about is this one here, right? This is the confidence interval for the population mean when the population variance is known. So we are supposing that you have a data x1 to xn, which are IID, normal, mu, and sigma squared, and we are assuming that sigma squared, which is the population variance, is known, right? So in this case, we want to construct a confidence interval for mu, right? So we start with this statement, which is a property I gave you. It's in the notes. So this implies this implies this, and this implies this statement here because of the graph that I mentioned, right? And this you can rewrite like this, right? Okay. And then you can rewrite this statement here in this form, and using the fact that these two are equal except for the minus sign, you can rewrite this in this form, and hence 100 times 1 minus alpha confidence interval for mu is given by this, right? This is the confidence interval for mu when the population variance is known. right? Okay, now I'm gonna do at least 3 of these today. Okay, I'm gonna restart because I did not actually give you the proof on Monday, but today I'm gonna give the proof for number 2, which is confidence interval for the population mean when the population variance is unknown. So we are supposing we have an IID data from normal, but with sigma squared unknown, right? This is a property I mentioned to you some time ago. It's in the scan notes. Just look it up, guys. So this implies the following, guys. It implies that the probability, let me show you the graph. If you look at this graph, guys, here, the bottom graph here, the probability that right? Do you see why? Because this has a t distribution, and this is the shape of the density of a t, the probability that this lies between these two limits, right, with a equal to n minus 1, must be 1 minus alpha, right? Right? So what I've done in this step is just to take the denominator to the left and the right hand side. Okay. Now this you can write like this. You have mu in the middle, right? And okay, and on the right hand side you will have x bar minus yes, and on the left hand side you will have x bar minus okay. All right, guys, I just rearranged this statement as a statement on mu, right? Is that okay? And in the next step, I'm gonna use the fact that these two points here are actually equal except for the minus sign. Okay, so you can write this right? That's I'm using the fact that t n minus 1 okay. All right. Okay, guys, do you follow me or not? So let me, if you don't let me know. Okay. So what you have here is, so what we can now show, what we can now say is the following, that hence, right, because of this statement, 100 times 1 minus alpha Ci for mu is the following. Okay, so this is the, if I may use the red color, so this is the statement that we have shown. We have proved that the confidence interval for mu when the population variance is unknown is equal to this, right? Is that clear, guys, or no? Yeah, please let me know. If it's not clear, let me know, guys. Okay, so let me also put this here. Okay. Now, the next thing I'm going to talk about is the following. So that's number 2. This is number 3. So far we talked about the confidence interval for the population mean when the variance is known, confidence interval for the population mean when the variance is unknown. All right, now the next thing we're going to talk about is the confidence interval for the population variance, right? Okay, so suppose you have IID data from a normal distribution with parameters mu and sigma squared. Now, you must remember this because I will be disappointed if you don't, right? Because we did this some time ago. Can you tell me what distribution this has? Come on, guys. Chi-squared with, what's the degree of freedom? Degree of freedom. Did you say 6? Oh, come on, guys. It's n minus 1, okay? So this is a result I mentioned in the class, okay, some time ago. I don't know whether you remember or not, right? Okay. Now what this implies is the following. If you look at the graph here, this one, because this has a chi-square distribution with n minus 1 degree of freedom, yeah. And these two guys here, between them, they have an area of 1 minus alpha, right? Okay? So this implies that the probability that right? Do you follow this? Because these 2 points are chosen such that the area between them is equal to 1 minus alpha. And since this has the cascade distribution with n minus 1 degree of freedom, the probability that this lies between these 2 points must be 1 minus alpha. Okay? So this implies now if you rearrange this statement as a statement on sigma squared, you will get the following. You see what I've done? I have rearranged this statement here as a statement on sigma squared. So this becomes this. Now from this statement, it is immediately clear what the confidence interval for sigma squared should be, right? Okay? So hence, all right? So hence, the conclusion is that a 100 times 1 minus alpha confidence interval for sigma squared is the interval given by this, right? So I'll put this in red. Right, so, okay. All right, guys, so this is number 3. Any questions on this, guys? Let me know what you do. What did I what? Sorry. Oh. Did I do something silly? You mean this line or this, which line? This line. What did I solve what? Sorry. I mean, from this statement here, it follows that sigma squared must be less than or equal to this divided by this, which is what I have written here, right? And from this statement here, it follows that sigma squared must be greater than or equal to this. Is this, hello guys, Is this the statement from this to this? Is it clear to any of you or not? Is it wrong or what? I mean, which part is not clear, guys? I don't know. I just rearranged the statements, guys, because when you have, if you take this inequality, right, you have sigma squared less than equal to this divided by this, which is what I have here. Yeah? And if you take this inequality, you have sigma squared greater than equal to this divided by this, which is what I have here. Anyway, think about it, guys. Think about it. Yeah? Is that clear to all of you? Some of you are still sleeping. What's up? Did you have assignment to complete last night or what? All right, number four is the confidence interval. So far we talked about two confidence intervals for population means and one confidence interval for population variance. And number 4 is now population proportion, right? Now, before I go ahead, I would like to tell you there are 2 tutorials this afternoon from 1 to 2 and 2 to 3. So if you haven't been to any of the tutorials this week, please do come, right? There's 1 to 2 in G209, 2 to 3 in G207, right? Okay? Okay. All right, guys. Do you know this distribution called Bernoulli? You heard about it or not? I'm sure you did, right? Bernoulli distribution is a distribution that takes 2 values, 1 or 0. So, for example, if you want to know the proportion of people who smoke in the UK, you go and ask everybody whether you smoke or not. 1 or 0. 1 if you smoke, 0 if you don't, right? And from that you can work out the proportion of people who smoke. And similarly, if you want to know the proportion of people who own a car in the UK, you go and ask everybody whether they own a car or not, 1 or 0, right? And from that you can work out the proportion of people who own a car, right? And so on, okay? Okay. Now, so we want to construct a confidence interval for P, right? Now, the thing here is the Bernoulli distribution does not have a simple form. I mean, it has a simple form, but it's not easy to work out the sampling distribution, right? So what I'm going to do is the following. Do you guys remember the expected value of xi for Bernoulli is p times, and the variance of xi for a Bernoulli is p times 1 minus p. And I'm going to write down something, right, you should recognize. Right. Do you know where this comes from? Huh? Do you guys recall? We did this in the class some time ago. What is this result known as, guys? Do you remember or no? Come on, guys. How come you say no to everything I ask? This is known as the central limit theorem, right? This is the CLT, right? Which says, if you look back in the notes, you say that the CLT says x bar minus mu. Mu is the mean divided by the square root of sigma squared by n. Sigma squared is p times 1 minus p, approaches the standard normal as n approaches infinity, right? So this is your mu, and this is your sigma squared. So you see, I'll replace mu by p and sigma squared by p times 1 minus p, right? Okay? Right? So what I'm going to say is the following. I mean, the sample size can never be equal to infinity. So I'm going to suppose that n is large enough such that the distribution of x bar this notation here means it means approximation. So I'm assuming that n is a large number, so that this guy here is approximately has a standard normal distribution, right? Okay, guys? Now, that means you should go back to the picture I showed you earlier. Let me find the picture. You go back to this picture. You remember this picture for the normal distribution, right? It implies the following, that the probability that right? This is z alpha by 2. This is z 1 minus alpha by 2. So the area between them is equal to 1 minus alpha. So this probability here is approximately equal to 1 minus alpha. The reason is approximate because we are assuming n is large enough so that this central limit theorem holds approximately, right? Okay. In the next step, I'm gonna do something cheeky, not something you see what I've done. I have replaced P. I have replaced P by X bar because in real life we don't know the value for P, right? And in order to construct a confidence interval, we need to know what P is, right? So I have replaced P by X bar. X bar is the mean, right? Right, and in this step I have taken the denominator to both sides, the left and the right. Okay. Right, and in the next step, I'm going to make this statement as a statement on P. All right, so this is what you will get. You get X bar minus X bar okay. So you see what I've done. I have rearranged this statement so that the statement it becomes a statement on P. P is we are trying to find a confidence interval on P, so we need to do this, right? Okay, now I'm going to use the fact that these two guys here are equal. I mean, this guy and this guy are equal except for the minus sign. Okay, so this will become right. Are you with me? So I have replaced minus z alpha by 2 by plus z 1 minus alpha by 2, which we can do because of this fact, right? Okay. Right, and let me put this over here. So the conclusion hence put this in a box. So this is the confidence interval for P, the population proportion. Is that clear to all of you or not? Yeah? Okay. All right, so just to summarize, we have talked about 4 confidence intervals. One is the confidence interval for population mean when variance is known. 2 is the population mean, confidence interval for the population mean when the variance is unknown. 3 is the the confidence interval for the population variance. And 4 is the confidence interval for the population proportion, right? Right. Right, the next thing we're going to talk about so far we only talked about confidence intervals for the next thing we're going to talk about is confidence interval for the confidence interval for 2 sample problems. Okay. Okay. The first one. Okay. Before I talk about the first one, suppose right. So we have, as you can see, we have 2 random samples. We have one random sample coming from a normal distribution with mean mu1 and variance sigma 1 squared. And we have a second random sample coming from normal distribution with mean mu2 and variance sigma 2 squared. And the 2 random samples are independent of each other, right? The first one, okay, number 1, the first one I'm going to talk about is the confidence interval guess okay? Right. I'm going to talk about the confidence interval for the difference in the 2 population means. Remember, mu1 is the population mean for the first sample, mu2 is the population mean for the second sample. So we are looking at the confidence interval for the difference when the population variance is sigma 1 squared and sigma 2 squared unknown, right? Now how to do this? It's similar to what we did over here, but it's a little bit involved. Now, okay, let x bar, all right, I shouldn't use x bar, okay, excuse me. Let x bar denote the sample mean, right? Of the xi's. All right. Now, what distribution will x bar will have? Right? I mentioned this 100 times already. It will have the normal distribution with parameters mu1 and sigma 1 squared divided by m. Right? And y bar, sorry, this is m, guys, m. If y bar denotes the sample mean for the second sample, it will also have a normal distribution with parameters mu2 and sigma 2 squared by n. Right? You follow me? I mean, so what can you say about the distribution of x bar minus y bar? X bar has this, y bar has this. So the difference will have, just look up in the properties I gave you. Right? The difference will also have a normal distribution with these parameters. This is one of the properties I mentioned a long time ago. And you probably, I don't know whether you remember or not, but okay. So what this implies is the following. This implies that this difference here will have a normal distribution with parameter 0 yes, all right, and this implies that the right? This implies that this expression will have a standard normal distribution, right? So the argument is the same. So if you go back to the figure I showed you, trying to fish out where it is, give me a sec, guys. You know the picture I'm talking about, this one here, here we are. If you go back to this picture here, right, this implies that the probability right? You follow me? Because this has a standard normal, the area between these two must be 1 minus alpha. Okay? Okay? Now, this you can rewrite like this. Okay? And finally, rearranging this, you will get this, right? Just give me, don't be in a rush to leave, guys. I know you always want to. Right? Right? This is equal to 1 minus alpha. Yeah? I know it's a lot of equations. A lot of equations here, but it's only one more step left. So now using the property that these two guys are equal except for the minus sign, right? You can write this as you can write this as this, right? And hence, just give me a sec, guys. Hence, 100 times 1 minus alpha percent Ci for mu1 minus mu2 is the following. Is big bracket x bar minus y bar minus right, comma, x bar minus y bar plus all right, guys, so this is the conclusion. Let me put this in a red. Where's my red pen? Oh, it's here. It's here. So just so this is the conclusion. This is the conclusion for the this is the confidence interval for the difference between the two population means when the variances are known. And by the way, if you have completed quiz 8, could you please give it to me now, please? And also, if you haven't been to any of the example classes this week, please come to the ones this afternoon. 1 to 2 and 2 to 3. mean this one? This one? Yeah, it's this one here. It's 2 cent. This one. Okay, it's this one. You want? Yeah, this one. 2 cent. Thank you, sir. All right, thank you, man. Thank you. You got it? You have a question, sir? You have a question? A question? Yeah, I will post it online for in a minute.
Yeah, okay.
But you want to take a picture?
Yeah, just because only one page, I mean, just that one.
This one? Or both?
Just that one page.
Oh, this one, okay. We can take this one. Or this one. Thank you, ma'am. Thank you. Oh, yeah. Thank you, thank you. You have a question? Yeah. I think it's alpha of 2. It's the same as this one, ma'am. It's alpha of 2. Because some people were confused. I think this is correct because if you rearrange this as a statement on sigma squared, this is what you will get. Did you see that or not? Yeah. Yeah, it is alpha by 2, yeah. Hello.
I have a question. The binomial distribution.
Yeah.
Why this?
In this example, because you only have one x, so the likelihood is the same as the PMF. But you don't have to take the product, because there's only one x.
Just
So one x. If you have like n data points,
So when I have a lot of x, I need to product.
yeah, you need to product. Yeah, yeah. Hello.
Just thinking about it, I don't think they did finish the question for me.
Oh, you want to take it back? Okay. Yeah.
I'll give it back to you
Yeah. Take your time,
in
man.
a 1 to 2 session.
Yeah. All right. See you.